I tucked it down in the corner.
All right, let's start again. So again, he's over here is basically saying that if you have a number e to power z, it will also be the same as e to power z plus 2 pi I. Basically, if you keep adding 2 pi I, it will be exactly the same. Okay, so even in something like this, so adding 2 pi to this will actually cause the imaginary, keep the angle basically rotating one more cycle, and that would use the same number. Okay, so this is the fundamental region of e to power z, basically from minus pi to pi, but then after that it keep repeating itself. Very good. So here is a typical problem. E to power z is 3 plus 4i, find z. Okay, so what's the plan?
Run.
This problem is not that hard in the final. You actually have to should try it at least. Okay, it's not really that hard. So we need to actually be able to see apple and apple. Alright? So in both sides you need to be able to look at apple and apple. So either turn this guy to Cartesian or turn this guy into polar form. So then you can put your eye and basically see the number. So we want the z, so which one is easiest? Turn this into Cartesian or turn this into polar? I think turn this into polar. If you make it a polar number, we'll be able to put our eye on the z. Right? 3 plus 4i. How we can turn this into polar? Magnitude time e to power I theta is r square root of 3 plus 4, right? So that's 5. And the magnitude is 10 minus 1, 4 over 3, plus and plus, it's in the first quadrant, then it's, again the calculation is in radian, so you get 0.927. So 3 plus 4i is 5 times e to power I minus 0.927. Is it apple and apple or not yet? If I said that the e to power z is 5 e to power I times 0.97, is that apple and apple? Because of the 5, right? We need to make this 5 go here as well. So how do we do this? If we make this 5 in the form of e to power something, okay? So take the ln, right? Ln 5 it become 1.6. So if ln 1.6, sorry, if ln 5 is 1.6, that means that e to power 1.6 is 5. And now here are two e multiplied by each other. So what do you do when you multiply e to power x times e to power x? It's e to power x1 plus x2. Right? Or basically this. So 3 plus 4i is now e to power this guy plus I this guy. Now this and e to power z is apple and apple. You look to this and say, obviously that's the z. So the z is 1 plus 0.60 plus I to power 0.927. Right? So in the quiz that we're going to have at the end of this, I will basically give you bunch of function in Z and then tell you exactly give me Z in the form of U plus IV. So I want you to figure that what is the real part and imaginary part of Z and tell me Z is 5 plus I3 or minus 3 plus I7. Okay? And this is one of the tools, you know, that you can use. You will have to turn the Cartesian into polar or the polar Cartesian depending on which is basically going to give you the way to go there. Alright? Questions? And so this is the solution basically that we just did, but he's doing it slowly. Alright? And he's saying that the answer is not just simply Z is 1.6 plus I 1.927. Why? Why Z is not just those guys? It could be those guys and
Plus 2.
excellent. Plus or minus 2n by I. So the imaginary part you can keep adding to it. Plus or minus 2n pi.
Is it literally plus or minus 2 n pi I or plus or minus 2 n pi?
Plus or minus 2n pi I. Okay. Because that basically the number basically repeat itself on the polar coordinates. Okay. Right. Sine and cosine, and we'll also do sine and cosine, and then len, and then that will be it. Right, so 13.6, let's go sine and cosine. So again, the Euler formula, now it should basically be straightforward. A to power I something, it's cosine that something plus I sine that something. Okay? And consequently, e to power minus ix, it doesn't matter, that's minus x, okay? It's cosine minus x plus I sine minus x. Well, it happened to be cosine x is the same as cosine minus x. So that's why you don't see cosine minus x here. But I don't want you to get confused. The reason why he's doing this is that he's trying to prove basically the formula for sine and cosine. But e to power minus ix, according to our rule, it should be what? Cosine minus x plus I sine minus x. Right? It's just that it gets simplified a little bit because cosine minus x is the same as cosine x, because remember cosine was even function and the sine is even function, so the sine is odd, so that's why it's minus I sine x. So why he's doing this? Because he wanna prove that when you look at those two formulas, and if you want to find out a formula for cosine x, all you have to do is add. If you add those two lines, the sign cancel, and you end up cosine x, 2 cosine x is this guy plus this guy. Or cosine x is this guy plus this guy over 2. That's this formula over here. Cosine x is half e to power ix plus e I to minus ix. Right? And the same thing for the sine. If you subtract this minus subtract this minus this, you get plus minus minus, and the cosine go away. So that's why the sine x is 1 over 2i, because you'll get plus 2i. 1 over 2i e to power ix minus e to power minus ix. Okay? So those are actually two famous equations. You should have you seen this before?
Yes.
Of course. Right. Okay? And this is not just for real number x and y and 7 and 3 and 2, but it's also for complex number. So cosine z is half e to power iz plus e to minus iz, and sine z is the same thing. So now this is a useful formula to know. Okay, so circle it in your book if they didn't already circle it for you. Yes, very good. And so you can tell then that if we actually put the 2i over here, so that it becomes cosine z plus I sine z, and add those two guys together, you will end up with half this guy plus half this guy, and the e to minus will cancel out, and therefore you prove the Euler formula again. in complex number. So e to power I z is cosine z plus I sine z. So that Euler formula is not only for real number but even for complex number. Okay, so I guess Mother Nature is really nice to us. So there is no two sets of formula, it's the same formula for real or imaginary. Okay, and by definition you know that the cosine and the sine is given by this. It's almost look like the cosine and the sine except for the I. So this was e to power ix and e to power minus ix. This is e to power iy and e to power minus iy. There is no I, just y, just the 7. So cosine 7 is half e to power 7 plus e to minus 7. But the cosine 7 is half e to power i7 plus e to minus i7. So the sine and cosine, they actually have the imaginary I in the exponent, but the cosine and the sine, they actually just real numbers. Okay. What we care about is the cosine z, the complex number, not just cosine, not just cosine y, but also cosine z. Right? So you know this formula for cosine x and sine x, right? But it's also, you can prove that it's the same for complex number. So the same formula applied for complex number, and the proof is over here. He's trying to prove that cosine z is cosine x cosine y minus I sine x sine y. Okay. And sine z is sine x cosine y plus I cosine x sine y. So how do we prove this? So you want this guy to be equal to this guy. So he start with cosine z. So what is cosine z?
1/2.
So we had it over here. So cosine z is basically half this guy plus this guy. So cosine z is half e to power I z plus I to minus I z. And so he wanna show that it's x and y and x and y. So he need to break e to power I z and e to power minus I z into the x's and the y, so that he can see the cosine and cosine. So how do you break it? Well, z is x plus iy and the other z is x plus iy. You got I and you got minus I. You take the I, multiply it in, so it become ix minus y and ix plus y, because the I go get multiplied by the other y here and become minus 1. So kind of the real become the imaginary and the imaginary become the real. At the end of the day he got e to power something, I something. And what's the formula for that? Cosine plus I sine. Right? And the same thing over here. And after that, you basically clear the dust. You pull e to power iy together and e to power minus iy, or actually just get the cosine x, I guess, together and the sine x. You will see this and you'll see that, and this is cosine and this is sine, and so hence proved. So cosine z is cosine x cosine y minus I sine x sine y, and the same procedure you can prove this guy by starting with sine z and plug the z, or plug this formula over here and turn the z into x plus iy and x plus iy, multiply the I, get real imaginary, break the e to power I into cosine and sine, and you will get it. I just want to make sure that you understand that step. So when I'm saying e to power ix minus y, how do you break this into real and imaginary? E to minus y, I first, take it out, and that's kind of a real number. E to power ix, right? And so e to power ix is cosine x plus I sine x. and this e to minus iy get multiplied by both of them because it's a real number. It's 7, 8, whatever. That's what you're looking over here. So that's this minus y, it's coming from this, and e to power ix, that's the complex number, and it's cosine x plus I sine x. Okay? And this is just basically, let's bring the cosine together and the sine together. So I mean, again and again we go through, this is the key turning point basically, how you can turn the polar into Cartesian. Okay? Right. So cosine z equal 5. Find z. What should we do? And when we say find z, you have to give him z basically in the quiz. I will tell you, put it in the form basically u plus iv, you know, real plus I imaginary. So what should we do? What you do when you say cosine z equal 5? Remember what's cosine z?
Your cosine z and then your 1/2 e to the I z plus.
There are many ways actually we can do this. We can also do this. We can say cosine x cosine y minus I sine x sine y, and then try to solve for the, look at the real and the imaginary and try to solve for those guys. Huh? But here's the cosine by definition is half e to power I z plus e to power I minus z, and this is equal 5. And so now I wanna apple and apple. So if this guy is like this, I would like also to be able to see real and Cartesian here. Alright? So how he's gonna do this? So he multiply actually the whole thing by e to power I z. And the reason for doing this is that he want to turn this into a second order equation in e to power I z so that he can solve for it. Alright? So when he did this guy become e to power 2 I z, this become e to power 0, which is 1, and this 10 become 10 to power e to power I z. So now this, you should think about this as basically kind of e to power I z square, and e to power I z and no e to power I z. So e to power I z is like our new variable. Let's call it lambda. And this is second order equation in lambda. Lambda squared minus 10 plus 1 equals 0. So to solve a second order equation with the coefficient 1, minus 10, and 1, the formula is minus b plus or minus square root of b squared minus 4ac over 2a. b is minus 10, a is 1, and c is 1. You do this and become plus 5 plus or minus square root of 25 minus 1 over 2. So this is a number, and it becomes basically 9.899 or 0.101. Depending is it 5 plus or 5 minus. What is that? What are those two numbers? Those are e to power I z. E to power I z, that was the unknown here, is equal to this or that. Alright? So when you look to this and you are saying e to power I z, which is e to power x plus I y, sorry, I multiplied by x plus power I y, right? E to power I z is e to power I x plus I y, which is e to power minus y plus I x, which is e to power minus y multiplied by e to power I x. And this guy is equal to what? 9.89? 9.899? Or the other guy. So if this is equal to this, obviously here is the e to power y, here is the real part, and this is multiplied by e to power ix is basically 1. The imaginary part is 1.
Where are the solutions?
So we are solving for z, right? But the equation actually is a function. The equation is e to the power I z. That's the unknown now. But we are really after the z. At the end of the day, we are after the z. But the equation given to us originally it was cosine z equal 5, and by using that definition, we are turning it into an equation in e to the power I z. We turn it into a second order rather than e to the power x and e to the power minus x. We said no, let's actually have it as e to the power x squared. So we multiply the whole equation, left hand side and right hand side by this e to the power I z, the unknown that we are after. This is as if we have an equation saying x plus 1 over x equal 10. So you are saying, no, I want to make it second order. Let me just multiply by x. What you will get, x squared plus 1 equal 10x. And let's solve for x. That's what happened here. Do you see this? This is the x, this is 1 over x, and this is a 10. Let's not call it x, let's call it lambda. This is the lambda, this is 1 over lambda, and this is 10. And we are after first the lambda, and then later this lambda, which is e to the power I z, we want to get the z out of it. Does this make sense? Why you are confused? It was lambda plus 1 over lambda equal 10. So we turned it into lambda squared.
Asking what is the
Changing the
solution?
variable doesn't help clarify.
Well, it just says this quadratic equation with the solutions rounded off to 3. I don't
Right.
know
So
what
here,
the solutions are.
what? Right. So you got this, right? This is second order,
Yeah.
and here are the coefficient, and here is the formula. Using this formula will give us two numbers. All this calculation will give me two numbers. This calculation, 5 plus or minus square root of 25 minus 1, will either give me 9.89 or 0.101. Okay? What is this number? That's e to the power I z.
Okay.
Now what's missing is, so once e to the power I z is equal to 9.89, what is z then? What's z? If e to the power I z is 9.899, how can I get my z? So we'll think about this as basically
Was that only
polar coordinates, as if it's polar coordinates. If it's polar coordinates, then it's 9.89, that's the magnitude or the real number, and it's multiplied by e to the power I 0. That's why it's 1, basically. Alright? So, good. So that's the polar coordinates. What's missing is that this guy need also to be in the polar coordinates. I need to be able to see r e to the power I theta here. R to e to the power I theta? I don't. I see I to the power I z. I want to turn this into magnitude and real. So let's bring the x and y out of the z. This is I multiplied by x plus iy. Okay, that make then ix minus y. If you bring the y in, the I in, become minus x plus, minus y plus ix. Well, this guy then is two parts, e to minus y, e to the power minus y, multiplied by e to the power ix. This now can be equated to this. E to the power minus y is 9.8, that tell you what's the y, and e to the power ix is 1, and that tell you the x. Right? So the x is 0. Right? E to the power 0 is 1. The x is 0, but not just 0. It's 0 plus or minus n pi. So x is plus or minus n pi, 0 plus or minus 2n pi. And when you say that e to minus y is 9.89 or 0.1, that tell you what's the y. The y is plus or minus 2.292. And that's the x. So here's your z. The z is basically this x and this y. No, the x is the real part and the y is the imaginary part. The x. So I know it's confusing because here that x was the imaginary and that y is real, but that's because only e to power I z. That what this I here is what flipped the x and the y. But z still, the z that we are after is still x plus iy. So at the end of the day, after we managed to get our y and we got our x, let's remember what those x and y are. Those x and y were actually, z is x plus iy. That's the x and y that we are solving for. So that's why here in the solution, look at this. He's saying z is plus or minus 2.292i. That's his y. And the x, which was supposed to be 0, but because of, where did this x come from? It came from the last step when we said that e to power ix is 1. Forget about where this x comes from. Just here's the new problem. E to power ix is 1. Give me the x.
0.
Because you are thinking, well, here's a complex number with only a real part, right? And 0 imaginary. I don't see any imaginary, right? So you are saying x must be 0. But also 2 by n. Because any x, 0 or 2 by n, or they will all basically end up being this guy. So out of this last step, he managed to get the x as, where? The x is 2n by, right? Actually plus or minus 2n by. Right? So now he got his x. Now he remembered what he was solving for. He wasn't solving just for x or y. He's solving for z. And z was x plus or minus, sorry, the z was x plus iy. So he put the x here as the real part of the z, and the y is written here next to an I to it.
How do you decide what? How did they decide to put e to the ix instead of equal to 1?
Right. It came from here. So when we were solving, let's look at this. We were solving for z, right? E to power iz. The equation turned out to be e to power iz. It's a second order of e to power iz. Because I can write this equation as this equation here that we finished with here in the blue. This can actually be written like this: e to power iz square plus e to power iz, sorry, minus 10 e to power iz plus 1 equals 0. Right, it's quadratic of this thing. I just want to call it lambda for now. I can call it Sam if I want to. Right? This variable that I'm solving for, this is second order for it. Right? How do you solve a second order? Here's the formula.
Quadratic formula.
Quadratic formula. What this formula will give me? It will give me lambda, which is, I know it's e to power iz. That formula give me e to power iz, or our lambda, as
5 plus or minus the square root of 25.
5 plus or minus square root of 25 minus 1, which turned out to be either 9.899 or 0.101. What are those? Those are e to power iz. I don't want e to power iz, I want z. So then he basically say, okay, so e to power iz is your 9.89. Can you get the z out of this? Yes, because e to power iz is actually e to power minus y plus ix. Why? Because the I get multiplied by the x become ix, and the I get multiplied by the iy become minus y. Okay? And the whole section we are talking about here was about this thing, that's the deal, that what is the exponential complex function? Not e to power x, but e to power ix. How does it look like? And it looked like this. It flipped the sign, kind of. or flip the real with the imaginary. Right, so once this guy, e to power minus yx, is equal to 0.1 or 9.8, what is the y and the x? And that's what happened here. We basically look at this and say, so it's a real part multiplied by imaginary part. But this number is actually equal only to a real number in front of our eyes here. So it must be that e to minus y is 9.8.
Because that's the solution to the real number.
Because that's the real number and that's the real number.
It just happens that that quadratic doesn't produce any imaginary solutions. Okay.
And the imaginary here, e to power ix, is 0. No, is 1. E to power ix is 1. That make x is 0. Or,
Plus or minus 2 pi.
right, 0 or 2 pi or 4 pi or minus 2 pi or minus 4 pi. Alright? So that's why equating this to this basically will tell you then that y is 2.29 plus or minus, and the x is 0 plus or minus 2 by m.
And you get the same answer whether you put the 9.89 or the 101.
Yeah, obviously.
The natural log of 9.9 is positive.
Right.
That's right.
So that's why. Plus or minus.
I think it's right.
Okay, guys?
Sorry, I need sleep.
And so that's
Because
how.
it's multiplied by z, you flip the imaginary and the real part.
Right, and so this is the detail of what we did. This is explaining it in detail. That when we said the e to power iz is this or this, that means that e to power ix plus iy is this, and this guy break into e to power minus y and e to power ix, and then I'm telling you, then the real is this and the imaginary is this. And so if the real is this, that make y equal to that, or that, depending on 9.8 or 0.1. If it's 9.8, it will produce the minus. If it's 0.1, it will produce the plus. And the imaginary part, that the fact that we don't see it over here, that means that it's 1, that make x 0 or 2 pi or 4 pi, or in general, this. And so you put the x here, you put the y there, and this is your z. Got it? Got it? Good. So, the cosine and the sine also follow the same formula that we have seen before for the real number. Alright, so the cosine is cosine, cosine, and you flip the sine, minus, plus, sine, sine. So when I was in high school, we would have to memorize all this, and we would have to go through all those kind of tricks to make our mind remember them. So that, because the exam was not open book. And you not only have to remember the format, you have to remember the sign too, and how the sign get flipped. And right, so as a result, then because of this, you can actually say y cosine square z plus sine square z equal 1 even for complex number. So that's nice. Right. Now the cosine and the sine, those are the same definition like for real number, right? Cosine z is half e to power z plus e to minus z. And sine z is half this guy. But here's a really nice trick. So cosine iz is cosine z. And sine iz is I sine z. And if you don't believe me, just put an I over here and you can see why would this happen. If the iz is a number, this has become I e to power iz. And you will have the same thing that we had in this example. Alright? So this could help really in solving the problem. So cosine, also iz is cosine z, and sine iz is I sine z. Alright? So why this is really nice? Because it allows you to turn this into a real and imaginary, kind of. Right. And those are the differentiation and the what is the tangent. It's the same definition that we have for the tangent, cotangent, the sec and the cosec, but the hyperbolic equivalent. And finally, it's 13.7. Let's look at the log and the power. So, natural log of z, right? So, If e to power w is z, then w would be the len z, just like the real number. Alright? And I guess he's just trying to prove it over here. And len z is obviously len r e to power I theta. And so just like how the len basically go into a multiplication and make it summation, so it become len r plus len e to power I theta, which become len r I theta. So len z is len r plus I theta. Okay. And so because len zeta is len r plus I theta, and we know that I theta is the same as I theta plus 2 pi n, I mean it's the same number, right? I theta and I theta plus 2 pi n and plus 4 pi n, then you can tell that len z then would repeat itself for any 2 by n. So len z is basically, this is kind of the fundamental principle or the basic one. But if you add 2 by n pi to it, it's just remain the same number. Okay. I'll let you play with this at home.
Oh, come on.
And again, so len z1, just like the real number, len z1, z2 is the same as len z1 plus len z2, and len z1 over z2 is len z1 minus len z2. Okay. And differentiation is also the same. It's 1 over z, just like in real number. Differentiation of len x is 1 over x. Differentiation of len z is 1 over z. Right? And z to power z, z to power c is e c len z. So how do you do this? How do you prove this?
Z to the C.
Z to the c is e c len z.
Suppose. Take the natural log of both.
Yes. So this become c len z, and then this becomes c len z. So z len c equal to c len z, so hence proved. What Shen is saying is that let's take the log of both sides. So if I take the log of this, it becomes c len z, right? And over here it become len of exponent. It's basically just this guy. So it becomes c len z. So therefore c len z is the same as c len z. Right? Yeah. Alright, and we are ready for the quiz.
Well, you are.
So I'll give you 10 minutes. So this quiz number 12.
Open book, open note.
Only open textbook.
No, it's coming up. Reading anything after the quiz.
Huh?
We'll drive home, I assume.
I will solve the quiz because I want you to. The reason why I'm giving you this quiz is not to take points out of you, just because I'm preparing you for the final, and so a problem like this will be in the final. So what is the problem? He said this is actually 3 problems. Okay, there are 3 problems. Alright? And he's basically saying find in the form of u plus iv. So this number, and this number, you want to figure out how much is this in real plus imaginary. You got it? So sine 2 by I, for example, you want to see that this is 7 plus I3.
This is rough stuff.
Are you lecturing after the quiz?
No, I'll just solve it after the quiz.
What is that what we consider z, the sine?
You can actually think of this as basically sine 2 by I is z, and I'm asking you for the real or and the imaginary, correct? Each one of those guys, it's as if I'm telling you sine 2 by I is z. What is the z? What is the u plus the I? The u. The u plus the iv. What's the real and what's the imaginary? You got it? Think about each one of those guys as if I am telling you z is sine 2 by I. What is the z? What's the x plus iy? Right? It's as if I'm saying z is equal to sine 2 by I. Find the x and y for me.
Oh, the z equals.
Brian, Batman, Matt Klein, Mark, Ray, Sean Freeman, Ricky Bell, Matt Fly, Inson Park, Harold Vince is not here, Mark Frey, not here. Brandon Rutter, Brandon, Jeff Snow, Holly's not here, right? Holly Carter, and Luke Cadilla, not here. David Lee,
Here.
where is it? And Eric Frank, Eric, and Hammer is not here. And Thomas Ali, and Eric McKinley, and Josh is not here, Joshua Hooton, and Zach Goodwin, and David Volk, David here, and Michael Simmons, and Aaron there, Aaron is here. So by the way, in the final, when I'm saying the exam is open textbook, you can also bring your tablet with an electronic copy of textbook, but you cannot bring your laptop. Because I want it to be flat in the screen in front of you. Alright? So no laptop. If you bring your laptop, then sorry, you'll have a problem. Genesis? Tiffany?
I'm so confused.
Huh? Mason, Nelson. Not me. Brian Swenson. Brian. Jack Kidden. Yeah. Greg Billick,
here, left. Sam, Sumner, and Walter Jacob. And Eric Wood over here.
Right, so this is the quiz. For those three cases, here is the z, and he would like to find out what's that z in the form x plus iy. You got it? Because I need the laptop. You just look here.